All right, thanks, Roberto. And sorry, guys, you have to listen to me for another hour. What I'm going to do today is I'm going to take 2 slides from Max, and I'm going to make a full-hour presentation. Okay, so it's going to be very, very introductory. So I hope that you're not going to get bored with what I'm going to talk about. And the lecture tomorrow will be quite advanced, so there will be a big difference between the two. Yeah, so today is, I guess, for the dummies. All right, so I wanted to start by just talking about machine learning and what is machine learning to put things in context. I guess a lot of people have talked about machine learning stuff, so probably this is also redundant, but bear with me. Right, so the first thing that we need to think about is if we want to solve a problem, right? So how can we solve this, this specific problem? Let's say, something that arises in medical imaging. So typically, as computer scientists, right, we write a program that basically does what we want to do. Right? And we hope that, that will actually give us good answers for what we want to solve. Now, in many cases, right, it's very, very difficult to just write a program that is going to solve this task for us, right? And then is where machine learning comes handy. And, these problems arises in, everywhere, right? So from image recognition, right, to, let's say, voice recognition, to something I really like, which is to have a personal assistant. Okay, now your guys are really, really going to sleep if there is no lights here. Anyways, so I would really like to have somebody, right, my iPhone or whatever, my little robot that can recommend me books, movies, how to dress, where to buy my coffee, etc. And these days it's very common that everybody has a startup, right? So I would like to know which one of all the ideas that we develop in the lab is the right one that we should invest our time. However, right, these learning systems are not going to be as we usually do, right? It's not going to be that we just write a program and it's going to do it for us. But typically what they do is they develop their own program, right? That is the program that's going to solve our final task, right? So that's a way to just very simplify, have a very simplistic view of what machine learning is. And how these systems come with that program is basically learning by example, right? So we typically give them, for a particular input, what is the desired outputs. So we give examples of how they should behave, right? Or maybe it's just by doing experience, right? By doing trial and error. And this is something that works really well in robotics, but maybe medical imaging is something where this should work as well. And if you think about it, this is how doctors operate, right? It's a little bit by trial and error, although it's scary. All right, so so the learning process is basically to try to incorporate the information about these examples into that program that the machine learning algorithm is going to come up with. Okay, so in terms of the tasks that we typically think about in machine learning, so we have supervised tasks, right, where the idea is that we give, for a set of inputs, examples, right, we give the right answer, right, and the algorithm has to learn from it. And it has to predict the right output, right? So we typically think of classification, right? And today I'm going to just only be talking about classification, where the idea is that we want to have a 1 of k or 1 of m output, right? There's also regression where this output is continuous and can be multivariate, right? We can maybe want to predict more than one output. Maybe something related to that is useful in medical imaging is unsupervised learning as well, right? Where the idea is that we don't know what the right answer is, but we still want to be using the data. And we want to use the data in order to sort of try to understand what we have out there and what are the regularities of this data, right? And we can do things like clustering, extract features, maybe later on will be useful for something else. We can maybe try to visualize what we have. But however, unsupervised learning is quite difficult because it's very difficult to come up with what is the right metric of when do I know that I'm doing good, right? Just saying that it looks good in the screen is not going to be a very mathematical way to encode a loss function. And something that maybe you guys don't see that often, but is coming little by little to computer vision, and hopefully soon it will also come to medical imaging, is actually reinforcement learning. So who in the audience has heard about reinforcement learning and knows what it is? Okay, so it's not too bad, all right. So the idea of reinforcement learning is that instead of having a supervised signal for every input, I'm going to know the right answer. What we're going to do is that we're going to sort of interact with the world, and at some point, I will receive some reward, maybe positive or negative, of whether I'm doing well or not. Okay, and this payoff is often delayed. It's not at every point in time I actually have an answer of was this correct, the move that I did right now. Okay, just to make sure that you guys know what this is, and I'm doing a digression because I'm not going to talk about the reinforcement learning, but it's so cool that I just have to show you guys. So here is I guess here is a computer that's going to learn how to play a game. Okay, it's an Atari game, and probably all of you guys have played this before. Right, so it's going to start by being quite clumsy. It has very little experience, right? And he plays like your maybe 4-year-old brother, right? And it's doing quite badly, I would say here. So after giving a little bit of experience, right, it's starting to do much better, right? So it's able to rebound the ball and get more points. And after a lot of experience, so here's what it comes up. Here's what it comes up with a solution, if my colleague helps. Yeah. Which is that you can build a hole, right? And that's the optimal move in this particular game. Probably you guys have, maybe you're too young to play this. I used to play this every single day of my life. Anyways. Right, so let me ask you the question. So in this particular game, what was this payoff or this reward? So it has a negative reward, which is when the ball goes off, right? It loses a life. And what's the positive reward? Every time you hit a brick, right, there is a positive reward because you want to pass to the next level, right? So this is how you train the system to actually do what it does. And this is not just, with very simple games. You can play, all sorts of different things. Again, I love games, so here is my favorite one. Right, so this is also trained by reinforcement learning. Okay, so here, Super Mario Bros. Right, it has to go around and pass levels and whatnot. And in this particular case, so this is what it learns as the optimal function. And in this particular case, the people that actually programmed this had the wrong reward function. Why do you think this is the wrong reward function? So what's happening with this guy? So it's not too bad, actually, but it's actually way too fast. Right? So it has a tendency to die too many times. Right? So if you put too much emphasis on that negative reward, then what it's learning is just to go crazy and go too fast, right? So it's not so important when you're actually playing games, but maybe medical imaging is a little bit more complicated, right? And you can do these sort of things for other things, and again, I just have to play these videos. They're just too cool. Okay, so let's set up these guys. And in this case, so these are some guys at UPenn, and you can learn to do all sorts of maneuvers with robots. So you can imagine training the instruments of the clinician or whatever to do all sorts of things, and this is really cool. Right. So you can imagine how many trials they did before they are able to do this, right? And I guess they have a big budget for buying robots at UPenn. I cannot do this in the lab. Anyway, so you can see here from the top view, it's actually quite cool, the kind of maneuvers that they do. Anyways, that was my little digression into the reinforcement learning. I'm not going to talk about it. It's just, I think, too cool not to show it. All right, so today is going to be more of the, like really simple, boring stuff. Okay, so bear with me, please. So the task is going to be multiclass classification, okay? And as I mentioned before, I'm just going to show you, very simplistically what neural nets, convolutional neural nets are. Right, so in this classification task, right, the task is to determine which discrete category every example belongs to. And so this is something that probably arises to every one of you, right, that you have one of these problems to solve. So when you want to solve one of these problems, the first thing that you think, so I'm going to give you a recipe of what are the things that you need to think about, okay? And then you can sort of reason about whether neural nets are the way to go or not. But before you get into whether to use neural nets or not, the first thing you need to think about is, what is your representation of the input? Okay? And this is not necessarily something that is fixed. Okay? It's something that you need to think about, what is my input representation such that it will be easy for the learning algorithm to learn. Okay? So these days, if you have images, convolutional nets are great. So images seems to be a good input representation, but maybe for your particular task, you need to do something to the input to start with. The output is also something that we don't spend enough time thinking about. I used to work for a long time in graphical models, and making graphical models practical was all about what is my output representation. Okay, what is my output representation such that I have efficient algorithms. Okay, so think twice before you actually select what your output is. So let's see some examples, right? So this is the canonical example that if you are in Toronto, you need to show some of this, right? Shame on me. So in this case, right, so what digit is in for every one of these images, right? There is 10 possible categories in this case, right? We all, love image classification, right? So here's my favorite animal, right? So is this a dog, right? So maybe, what about this one? Who thinks this is a dog? Who thinks this is not a dog? You're all wrong. This is a dog in China. It does exist. All right, so things that people care about, whatever. Maybe if you have diabetes, again, will I succeed? All right, so that's about the input and the output, right? The next thing that we need to think about is our model hypothesis class, right? So what kind of function or set of functions or model should we use in order to solve our task? And this is not just trial and error and go brainless into it. It's more about what do you think could actually represent your data, right? You guys have insights about the data that you're going to work with, right? And it's important that you try to use those insights, right? Even in discriminative models, you can still use prior knowledge. Okay. So in this particular case, I've chosen the simplest model that one can have, one of the simplest models, which is just to use a linear model. Okay, so a linear model is parameterized with a set of weights, as well as the bias or intercept here. Okay, and X, remember, is your input, and Y is your output. Okay, so here is just a depiction of this problem, right? So in this particular case, we have binary classification. We have two classes, right? We have a two-dimensional input, right? This is the first coordinate, second coordinate of the input. And I just color-coded here. So these are training points, right? I color-coded the answer, right? The particular class they belong to with a particular color, right? And when we do linear classification, right, the idea is that we want to compute a hyperplane, right, that separates the data into, separates the space into two half spaces, okay? What is on one side of the hyperplane and the other side of the hyperplane, right? And so what does it separate into two spaces? Because the way that we do classification is by looking at the sine function once we have this linear model, okay? And that basically gives us the two separated hyperplanes, sorry, the two sides of the hyperplane. And the question is, for the machine learning algorithm, we want it to actually end up with the answer of what is the best hyperplane for our particular data, okay? This is what the machine learning algorithm is going to have to do for us. Right, we're not going to just input some weights by hand, right? Because maybe we have more than 2 dimensions, right? So it's going to be difficult for us to do, right? So we want to learn what will be a good set of weights and biases for our problem, okay? So what do you guys think is the best hyperplane? Any ideas? All these seem pretty good, right? They seem to classify perfectly the data. So, but we still need to give some information to the algorithm, right, so that it comes up with, as good as possible of a hyperplane. So that's the concept of the loss function, right? So when people say, okay, what is your loss function? This is what they mean, is what is the function that the machine learning algorithm has to minimize such that it comes up with an answer for your problem, okay? And this is, again, something that you need to think about. Not just use, the first one that comes out of the box. Think about what would you like the algorithm to be doing for you, okay? All right, so one example, right, for those of you that were doing support vector machines, right, in your previous life, right? So what would you like to say is that you want to minimize the minus margin, right? You want to maximize the margin, which is the distance between the plane and the closest point for every one of the classes. Okay, this is one particular loss function that we can use. So once you have the loss function, right, so you have to come up with an efficient algorithm and clever algorithm to do this minimization. And that's most of machine learning is actually trying to do that. Okay. So the other thing that you need to think about is what is your metric, right? And what is this thing? It's basically how are you going to evaluate whether what you learned was actually a good model, right? And so this is something that is kind of funny, right? Because probably you're thinking, what is the difference between the loss function and the metric? Any ideas why I'm talking about two different things? Why is my loss function not my metric? Who knows the answer to that? Or should it be the metric and that's it? Don't be shy, please. I'm equally hot and unpleasant here as you. Right? So we will always like to have the loss function to be the metric, but this metric might not be differentiable. This metric might be very, very difficult to optimize. And this is why typically the metric, which is, you know, when we participate in a benchmark, that's how we evaluated it, is typically not how we actually train our models, right? We train with cross entropy, log likelihood, you know, max margin, and all these different things. And those are not how we are evaluated at test time because it's very difficult to train with those functions that we are evaluated at test time. Okay? But you know, it's also very important to think about the metric when you select the loss function. And tomorrow I will show you some examples of that. All right, so I started with a very, very simple model, which was this linear model, right? And the question now is, how can we make this model more powerful? You probably all know the answer, right? If linear model is too simple, what do? We do nonlinear, right? That's, okay. Just contradict what I said before, right? And it will be the right answer. Right, so there is many options into, you know, how to use nonlinear functions, and they are typically categorized into two sets, okay? So two types of approaches. So before, you know, a couple of years ago, right? Before 2012, right? Everybody used the kernel trick, right? Or almost everybody used the kernel trick. And the idea is that what we can do is we can take our inputs, we can pass it through some nonlinearity that is fixed, okay? Maybe it has some properties. We can compute this feature map, and then basically we can optimize a linear function on that different space phi of the input x, okay? And the kernel trick is just that for a lot of these algorithms, you don't even need to compute phi in order to do optimization, in order to estimate the model. Okay, and that's actually very useful because, for example, when you use an RBF kernel, phi is actually infinite dimensional, so you couldn't even compute it in the computer. So now these days, that's old-fashioned, right? Almost nobody uses that anymore, right? So what people do is actually to use deep learning. And what is the difference is that here this feature function was actually fixed, right? And now we are gonna, and then you learn a linear mapping on that high-dimensional space. What we're going to do now is actually learn that mapping, okay, from scratch. And that's why neural nets are very, very powerful, right? Because they can actually predict very complicated nonlinear functions. Okay, is this clear? Right. Everybody has this already. All right, so if you want to do neural nets, the very interesting thing is that you only need to know two algorithms. And I promise you that you knew these two algorithms beforehand, even if you have never seen a neural net, okay? You just didn't know that they were called forward pass and backward pass. You just used them before, you know, in your bachelor's degree, both of them. So forward pass is used to perform inference, and the backward pass is used to perform learning, okay? Where the forward pass will be inside the backward pass, because as Max talked before, to do learning, we always need inference, okay? And so what are neural nets called, what is it called? Deep learning, right? Because before we used a black box for our classifier, now we have a set of black boxes concatenated, right? So they are very deep, right, these black boxes. Anyways, that's my 2 cents on how deep learning is. Right, and luckily I got just tenure in Toronto, so they will not fire me after saying these things. All right, so let's look at the neural nets. So they're gonna, I said I'm gonna compose a set of black boxes, right? So the idea is that you're gonna compose simple functions to create very complicated functions, right? That's a very, very powerful idea that was out there, for many, many, many years, centuries, whatever. And we are never gonna compose linear functions because a composite of linear functions is linear. So there was no point in doing that in the first place. Okay, so this is my little running example that I'm gonna be given for showing you the forward pass and the backward pass. Okay, so here is a little neural net with 2 hidden layers. Okay, and in this case, it's gonna be a fully connected neural net. Okay, so the simplest, going back to the 80s. So X is gonna be the input, right? Y is gonna be the output, what you wanna predict. HI is going to be the ith hidden layer, okay? And W's are the parameters, and B are the biases, which are also parameters that you want to optimize, okay? So is this depiction clear, right? So it's very, very upfront, right? So the idea is that we have these black boxes, and these black boxes perform very simple operations. In this case, linear mappings followed by some very simple nonlinearity, and this is pointless nonlinearity for every entry. All right, so let's look at how to do inference in this net, right? So the assumption, if we're going to do inference, is that we already have the weights and the biases, right? We have trained somehow our net, and given a new input, we want to estimate what the output is, right? What the model is going to predict. So the way that we are going to do this is, again, as I mentioned before, by just composing functions, right? So, so the idea here in this particular case is that we're going to have we're going to compute the activations in the hidden layer, right, by doing the linear mapping followed by the nonlinearity, which is the max, right? We will get the activations in the hidden layer, and then we will compose the next function, right, by taking that output, passing through the linear mapping, and then passing through the nonlinearity, okay? And then we will get the output in this case by just following this linearity, okay? So is this clear? So this is all it is for inference in neural nets, right? I'm sure that in linear algebra you did something like this, right? Even in high school. Okay, so very simple, right? How you compose functions is just by substituting what you compose with and do it, step by step. All right, so neural nets have many ways to represent them. This is the typical way that everybody represented them before, when you didn't have so many millions and billions of weights, right? You could still do this because you have maybe 10 hidden units, right? And this is just to say it's fully connected, meaning that every input is going to influence every one of the outputs, okay? Anyways, so all these things just mean the same thing. Now, the nonlinearity that I use is something that is very useful these days that almost everybody uses, which is this ReLU, this rectified linear unit, which is a function that looks like this, okay? And which basically says that I'm going to output 0 until I cross a threshold, and then I'm just going to go with the same, with a linear value, which is the same value as I had it before, right? And so if you think about after composing all these functions, what this thing is doing something really, really intuitive that we were doing already many, many years ago as well. We just didn't call it neural nets, which is to think that if you look at the space, let's say manifolds, for example, right, the space of all my points, I can do very simple approximations if I do it locally. And locally, they can be locally linear, right? So this ReLU, what it's actually doing is partition the space into chunks, and for every chunk, you have a linear function. Okay, so again, it's something very, very intuitive. Right, so also we, call these neural nets as graphical representations, right? And the idea is that the way to get classification on the top is by composing the different activations that I get in the different layers, right? So the hope is that I can get more interpretability. I can get parts. If you think of objects are composed of millibit parts, which are composed of simple edges. Things like that, right? So hopefully I don't need, maybe, exponential explosion of things. I can just do it with a hierarchical representation. All right, so that was all for inference, right? It was very, very simple. It was something that everybody knew anyways. And so let me show you learning, which is again something that you guys already know beforehand as well. So I just simplified the net. If you look here, I remove the biases just for the sake of this conversation, okay? And so the idea is that we want to estimate the parameters, right? The biases as well as the hyperparameters. So what are these hyperparameters, and why don't I call them parameters, right? So there are things like number of layers, number of hidden units, type of nonlinearity to put there. These are all choices that somehow I need to do, right? And unfortunately, most people do this in a manual, you know, we call it graduate student descent, okay? Where the idea is that you try here, you get some sense, as Jeff does, you do like this, right? Comes out with some values, you try again and whatnot. So these days, maybe it's not so much used, but it's really, really useful to use Bayesian optimization to also optimize automatically all these hyperparameters. So use Gaussian processes to do this. So I'm not going to talk about this at all, but just ask me if you're interested in knowing more about that. So we will call them hyperparameters. We will, you know, forget they exist. We will believe that, you know, somehow you're going to set them for the sake of this talk. Okay. All right. So then what I need to do, right, is collect data in order to train my model, right? I need to estimate these weights. So I'm going to collect. This is a supervised task. I have a discriminative model, right? So I need inputs, right? I need examples of what the input looks like and what the correct output looks like. Okay. And that's what I need to give this neural net in order to estimate these weights. So typically, how we encode the outputs, let's say in this case it's multiclass classification. I have k different classes. I do it with a 1 of k encoding, which is to say that I'm going to put zeros everywhere for each particular example, but I'm going to put a 1 on the correct answer. Okay, so if my class is the kth class, right, I will have a 1 in the k inputs for the output vector, right, and I will have zeros everywhere else. Okay, so right, remember my recipe? So we have the inputs, we have the outputs, we have the model now. It's this very simple 2-layer neural net. Now we need to come up with the loss function, right? So typically we do, as Max said before, empirical risk minimization. So the idea is that we're going to just minimize the loss that we incur for every one of our examples, okay? And we typically also add a regularizer because these models have too many parameters and they are too powerful. And this regularizer basically says that, you know, don't go crazy, you know, come back to Earth and do something simple. All right, so what do we want to use as this loss function, right? So what do you guys will use for training neural nets as loss function? That's right, you were listening. So it depends on the application, right? But what's the, you know, what's an example that of loss function that you will use for classification? What do you all, you know, all of you guys use? You use maximum likelihood, right? It's called cross entropy in neural nets, but it's exactly the same thing. You can show it mathematically, it's the same function, okay? The way that it's used. Okay, so again, we would like to use the task loss, right? Depends on applications, but you know, it's too difficult, so we will come up with what is called surrogate loss, and that is going to be, it's going to be typically convex, and let me explain what that means. It's going to be convex on the outputs of the neural net, okay? And so this comes out of the fact that all these loss functions were used before, right, for all different sort of classifiers that people were using, okay? And so we have very, very simple loss functions. So now that neural nets are very complicated and nonlinear, you can think of, you know, more complicated loss functions if you wish. Okay, so maybe we should go a little bit farther away from just using cross entropy and using mass margin. Okay. All right, so that's what I mean by typically convex. So it's not going to be convex on the parameters. Okay. All right, so we mentioned before, right, log likelihood. In order to do log likelihood of cross entropy, I need some notion of probability. And in my little neural net example, right, I didn't have any probabilities. So how do we translate a neural net into a probability function? We use a softmax, right? The only thing that is a softmax is that we're going to exponentiate every entry, right? And we're going to just divide it by the sum of all these things, of these exponentiated entries. And the idea is that why is this computing a probability distribution? Because it's always positive, and it sums to 1 when I sum across all possible values of the output. Okay, is this clear? Right, so this is just a simple way to create a probability distribution. All right, so then I compute my cross entropy that looks like this, and again, this is just the same as minimizing the minus log likelihood. Okay, why is it the case? Because this t function, the way that we created, was 0 everywhere, but it had a 1 in the correct answer. And that's exactly what log likelihood is doing. Okay, that's why it's equivalent. Okay, so for those of you that were listening to Karsten, for example, lecture on graphical models, can somebody interpret what the graphical model is here? There is an inherent graphical model in this neural net. So apart from Giovanni, somebody else wants to give it a try? No? I guess Giovanni. So it's not a mixture of Gaussian. So it turns out that this guy here is nothing but a graphical model with a single random variable which has k possible outputs. Okay, so when you do logistic regression, right, it's the same graphical model, and the only difference is that here we are actually learning these feature functions phi. Okay. So remember, yes, a single graphical, a single random variable, which is the output of the neural net. Okay. And this guy here is nothing but the partition function of that very simple graphical model. So this will become very, very handy in my talk tomorrow. Okay. So try to remember that thought, and hopefully you see that this is the case here. All right, so how do we train these things? We're going to use gradient descent, okay? So I just put a figure here. I'm sure that everybody knows what gradient descent is, but is there anybody here that doesn't know what gradient descent is? And please don't be shy. Okay, 1, great, 2. All right, so here's the slide for you. Okay, so here is a function, is this function here, and this thing here is the isocontours, which means the points where this function is actually has equal value. Okay, and what gradient descent is typically doing when you want to minimize a function is basically you're at a particular point in the function, okay, and then you look at the gradient, and the gradient is the maximum local direction of ascent. Okay, and you just go in the direction of the minus gradient. Okay, you go for a little bit, okay, and then you recompute the gradient there and you continue going. So it's a very, very simple first order method iterative process. And the hope is that we'll convert you to some local minima. Okay. All right. So this is how we train neural nets by using this simple gradient descent. Okay. So the idea is that at every iteration, I need to compute the gradient of the weights. Okay, or the Jacobian in this case of the weights. And if I'm able to do this, right, I will update my weights by taking the current estimates and just corrupting with the information that is coming out of the gradient. Okay. Is that clear? Right, it's a very, very simple procedure. And the backward pass, this backward algorithm, is nothing but, this back propagation algorithm, right, is nothing but an efficient way to compute this gradient here. Okay, and I mentioned before that it's something that you have seen before. So back propagation is nothing but the chain rule. Right, it's just a fancy name for something that you guys all know about it. Right, so let's look at the, how to do this here, right? So remember, when I minimize this loss function, I'm going to concentrate on a single example and over this. Okay, I'm going to leave the regularizer and just look at the loss function for a particular example because it decomposes as the sum of loss functions. Okay, so it's very, once you have the gradient for one, right, you just sum the gradients for all of them. All right, so we computed the probability distribution by exponentiating, right, and we can compute the loss function, right, given t's, which are the outputs that are the ground truth for the examples, right. So now what we need to do is compute the derivatives of the loss function with respect to all the parameters that we have, okay. And the way that we're going to do this is by doing little by little the derivatives over the different elements of interest and going backwards. Okay, because the chain rule tells us that we can use what we have computed so far in order to compute gradients that are, deeper down, which is the opposite of deep in neural nets, right? As we go towards the input. Okay. All right, so that's all that it is to backpropagation. Okay, so here I just put for you the partial derivative of L with respect to, or the loss function with respect to the output y. And it turns out that it has a very, very intuitive function, intuitive form, which is basically to say that I want my probability distribution to be peak and to put all its mass in the correct label. Okay? And this is something very dangerous if you think about it. Okay? And so we should think about whether this is the correct loss function when we want to train neural nets. And the reason why I'm saying this is that, you know, we can make the networks super confident on something that maybe it shouldn't. Okay. And the more happy we are is when we put actually all mass in this delta function. Anyways, so that's what this partial derivative with respect to y is doing, and then we're going to continue, you know, going backwards. Okay. So now we look at what is the partial derivative of the loss function with respect to all these hidden activations. Okay. So who knows the answer of this? Come on, guys. Right. So what do we need to do? So sorry, I start with the weights. Same thing. Right. So we only have a linear mapping here, right? So it's very, very simple. So we do our little chain rule, right? And what's the answer? Right, so yeah, we just copy what we had before for this term, right? This is a linear mapping, so we only need this thing, right? So it's very, very simple. Are you guys with me, or you're really bored? Yeah? Okay, great. Right, so how do we do this? Same thing, right? We compute the partial derivatives, right? We compute the chain rule. And what's the solution to this? It's again linear, right? So it's very simple. Right? In this case, it will be the weights, right? Times what we have so far. Okay, so now we have compute the derivatives for the weights of this guy here, right? And we need to continue to compute derivatives with respect to the weights here. And the way that this works in neural nets is that we always compute the derivatives with respect to the weights at that layer and with respect to the inputs. Why do we do that? Because the derivatives with respect to the inputs are going to help us continue doing the chain rule. Okay? Right, so that's what we have to do at every point in time, right? And again, so in this particular case, is with respect to the weights and as well as with respect to the activations. Okay, and then we continue this way. All right, so that was very simple, right? Typically with the functions that we have, we can compute them analytically, right? So actually our little program to train neural nets is only a few lines of code, typically 10 lines of code, okay? And everything around is just wrappers for your data, okay? The backpropagation algorithm is really, really trivial. All right, so as I said before, right, we want to minimize this and we use the backward pass to compute efficiently the gradients. And recall that we needed to estimate, if you remember here, we needed to estimate this, and this is nothing but the forward pass. So inference is always part of learning, okay? Also with these discriminative models. All right, so I'm going to show you a little algorithm box that will, hopefully you will remember for my talk tomorrow. And the idea is that we compute the forward pass to compute the activations of the last layer. I'm just going to call them F, because I will use this for graphical models tomorrow, okay? Then I can compute the softmax, that's this P of y given x, so it's a discriminative model, right, and given my weights. This is the forward pass, right? Once I do my forward pass for every training example, I compute the backward pass to compute the gradients for every one of the weights, right? And then I add all this up, right? I add also the term that comes from the regularizer, and I update the parameters. Okay, and I just continue iterating. And this is basically, when you use all these packages, what it does. Something really, really simple that all of us understand. Okay, there is nothing, you know, completely crazy here. All right, so Max spent quite a bit of time into some time at the end talking about what happens when I have big data, right? So in this case of here is explicit is that n is the number of examples, right? If I have billions of examples, I'm not going to be able to compute this. I have billions of weights, billions of examples, right? With luck, nobody's going to be able to graduate before, you know, your program stops, right? So what do I do is I use MiniBatches. So what is MiniBatches? Is you can think of it as, instead of using all my examples, I'm going to sample some of these examples. And since this thing is the average of the gradients, so long as this average that is coming out of a subset of the examples is pointing on the right direction, I'm doing a good job, right? And that's the idea for a stochastic gradient descent, is that so long as my MiniBatch is big enough and it's giving me, the right direction of the gradients, right, I'm actually going to do a very good job without looking at all my training examples, okay? Now, typically we would like the MiniBatches to be bigger, but we are constrained by hardware, right? And this is why our MiniBatches to deal with images are very, very tiny, okay? And then we do other things like momentum and whatnot, but I will not enter into those details. Okay, so this is called a stochastic gradient descent. Again, very, very intuitive, very simple what this is doing. All right, and I say sampling, but this is not really sampling, okay? Anyways. All right, so the other thing is how do we deal with big, large input spaces, right? So this is how to deal, this MiniBatches is how to deal with a lot of training examples, and now we need to come up with a way to deal with when we have an input that is very big, right? An image has millions of pixels. You guys have volumes, right? There is one more dimension that multiplies, right? So maybe this is a billion, pixels or whatever, right? So how do we deal with this case, right? So we were using fully connected layers before. So how many parameters I had for every hidden layer? So it was the number of inputs, right, times the number of outputs, right? That's a lot of parameters, right? So we're not going to be able, if we have, let's say, 1 billion inputs, right? That's already, even if we use a single neuron, right, it's already going to kill us, right? So what do we do? Well, the first thing that we can think of is trying to have a locally connected layer. Okay, so in images, the interesting thing is that the coordinates are not just set at random, right? They have neighborhood. The pixel that is next to me has a meaning with respect to myself, right? So maybe what we can do is try to have local filters that multiply in my linearity, and then that will simplify, reduce the number of parameters, right? So here's an example where for every output, I'm only going to look at a subset of the inputs, okay? So in that sense, I'm cutting this dimensionality of the inputs. Now, is this a good idea or not? Here I'm training different filters for different regions of the space. So if I have my images registered, and maybe you guys have a lot of the images registered, let's say MRIs of brains, right? This is a very good idea. It means that I'm gonna learn features that are specific, let's say, for brain matter, or specific for, here's my anatomy, it's not very good, but for whatever tissues that are out there in the brain. Shame on me, I did medical imaging a very long time ago, yes. Before my master's, anyways. Right, so for real, standard images, this is not a very good idea in general, right? Because, things can appear everywhere in the image, right? So what we typically do is that we're gonna share these filters that go across the image, right? And this is exactly the notion of convolutions, right? And this is why convolutional neural nets are very powerful, is because we're gonna use the fact that the statistics are the same everywhere in the image, and I'm going to apply the same filter everywhere in the image. Then I'm going to share parameters, right? And I'm going to prevent overfitting because I'm going to have much less parameters than if I have a fully connected layer. All right, so this is a very simple depiction that I stole from Macarena Ranzato. And the idea of convolution, right, everybody knows, but is that I'm going to place my filter at a particular location, right? I'm going to do the inner product of the little filter with what it overlaps in the image, right? And that will give me a single value in the next layer, okay? This is the computation of H, right? These hidden activations. And I'm going to move this thing, but I will use the same weights, right? And I will compute the next value, and I continue moving, and I end up with, what I have at the end, right? And then I'm going to use many, many, many of these filters, right? And maybe I use pooling, right? Max already quizzed you on this, right? So the idea is that now from a set of local hidden nodes here. I'm gonna take into account all their values in order to come up with a final answer for the next layer, okay? And this can be max pooling, average pooling, or really, really sophisticated pooling operations. And I think this is very exciting to look at sophisticated pooling. All right. Right, and you can think of pooling as a way to increase your receptive field size. So the receptive field, right, is every one of these neurons. How, if you look at where in the image it has influence, right? What part of the image was used in order to compute as I go further up, right? The receptive, you can show that the receptive field is actually increasing exponentially. But also its value decreases exponentially as I go away from the center. And what this pooling operation is allowing you to do is to increase the effective receptive field size. Okay? That's why it's actually used and it's very useful. And also get some invariances. All right, so in the last 5 minutes, I'm going to just show you this with pictures, okay? And just reiterate on the same idea. As I mentioned today, it's very, very introductory. All right, so again, here is the favorite animal. So here's my dog. I mean, not my real dog, I don't have a dog. But so here's the dog. And so typically, right, when you started in this field, right, of medical imaging, or you took a class in image processing, right? And the first thing that everybody teaches is filters, right? So in this case, let's say that we want to compute gradients, let's say on the vertical or horizontal direction, right? The simplest filter that one can come up with is this thing here. In this case, it's going to compute vertical edges, right? And the next thing that we learned in class was that, well, a single filter might be a bit too restricted. Maybe we have a filter bank, right? And by using a filter bank, we can do more sophisticated processing, right? Maybe you can do one filter after the other or whatever, right? So in that case, given an image, right, that I have over here, I'm going to compute an output volume, which is going to be one of the dimensions. So the dimensions are going to be the size of the image, right? If I don't think of the border effect, times the number of filters that I use, okay? So this is the output of your filter bank, right? And so you can think of these convolutional nets as doing nothing but sophisticated filter banks, okay? So here's an example where I have 224 by 224 image, and I have 3 channels. Okay, so when I'm going to do these convolutions, my filters are 3-dimensional. Okay, so they're going to be, in this case, 11 by 11 by 3. Okay, and in this case, I'm going to have 96 filters. Okay, and I'm going to use something which is called a stride. Okay, what it means is that instead of doing convolutions every pixel, I'm going to do convolutions every x pixels. In this case, I'm going to do convolutions every 4 pixels. Okay. And the idea here is that I'm going to try to do less processing. I'm going to try to reduce my input because as I go deeper, I want to maybe at some point arrive to a fully connected layer, which will have a lot of parameters, right, if I don't reduce the size of this volume. Okay. All right, so I do this stride, and since I have a stride of 4, then I basically divide by 4 the dimensions of the image. Okay, is this clear? All right, so then I'm going to do some pooling, right, as I mentioned before, to get some invariance, and I get the first hidden layer. Okay. Now I'm going to do the same thing. I'm going to take the output of this volume, right? I'm going to apply all of the filters. Let's say now 5 by 5. Okay. So this will be 5 by 5 by 96. They're again 3-dimensional filters. Okay. And how many filters did I use to create this volume? Huh, guys? Who is awake? 256, right? What was my stride? What was the stride here? 2, right? I reduced dimensionality by 2, more or less, right? Roughly. Great. And then I keep on doing this thing. Okay, I use some max pooling in between. I put some, what I didn't say here is that I can use a ReLU at the end of this, okay? And then I start putting fully connected layers, okay? And I decided to put 2 fully connected layers of size 4096, okay? Sounds like an appropriate number, okay? And at the end, I put an output that is 1,000 dimensions, which is going to be the output of my softmax. Okay? Somebody identify what this is? No? AlexNet, right? Here it comes. So this is AlexNet. So how do we train this? I just explained you before, right? We have examples, in this case images, let's say a dog, and the output says that it should be a correct dog, right? So we use back propagation, right, given this cross entropy, right? We train in the same way. Here is a cat, here is a boat, right? I have a whole bunch of examples, right? And this is how I train this network. And how do I do inference? Is again by doing all these processes one after another, right? Until I get the output here, which is the probability of this being a cat, probability of this being a boat, okay? All right, so I need a lot of examples to train this. In this case, I use ImageNet. I have 1,000 classes. This is why I have 1,000 dimensions of the output, right? There was a reason why I had that. I let it run, and then, you know, until I'm bored, maybe a week, 2 weeks, depending on my GPU, right? And the interesting thing also to think about is, so here's a different depiction of AlexNet, is that if I think of the number of computations that this net has, computations are mostly in the convolutional layers. Okay, so here you see I do like millions of computations, while parameters are basically at the top layers, okay, the fully connected layers. All right, so here's Jeff, and I call this the 2012 computer vision crisis, right? And how the supervision system beats, you know, everybody else's system by a lot, right? And this change skew computer vision these days, for good or bad. Okay, there's good things and there's bad things, and I'll let you, you know, hopefully you guys are in the good side and not the bad side. All right, so it turns out that these networks are great, right? But what I show you is very, very simple, right? What we're actually doing here. So it's not much of you know, craziness here, right? So the interesting thing is that now, if you look at computer vision papers, and I'm sure that medical imaging is starting or is at the same point, is that everything is deep, even if they use a shallow network. Okay, it will be deep in the title, right? Of course. Otherwise, the reviewer is going to ask you, why didn't you use deep learning, right? And you have no answer. Right, so the other thing is that, you know, to my despise, I guess, companies and now leading competitions. So this is a slide from a year and a half ago. Pascal is led by a company right now, right? So this is old, unfortunately, even Pascal. I guess ResNet is Microsoft Asia, right? All right, so the other thing is that, you know, all these companies are stealing, you know, most of professors, right? And also all my students, even after their masters. So it's really, really annoying these days. I don't know if there's somebody from Google here, but you're going to hear me. Right, so this is not recorded, is it? All right, so neural networks, right, are great, and they can, you know, we can train them, and we need a lot of power. I said that, you know, 2 weeks. So what's happening now, right? So since we need a lot of power, what can we do about it? Any ideas? This seems annoying, right? We're gonna, you know, kill the whole planet. A very significant portion of energy is Google, and I'm not kidding. Right? So what can we do? Build smarter algorithms, maybe? Do compression these days, maybe? What is everybody else doing? Hey, let's buy more GPUs, right? All right, so then, you know, one can use more layers, right? And it turns out that the more layers you add, it seems that there is more and more gains in performance. So this is BGGNet, I guess Andrea will be talking about. ResNet, I only put here the 34 layer because it didn't fit in my screen, right? But now you can do more than 100 layers, 1,000 layers, right? You can go crazy. And I guess there will be a reading tomorrow about this particular algorithm, right? But what seems to be happening is that the more computation that you add, so long as you have a good way to regularize and a good way to sort of interpret what's happening, then, you know, the more, the merrier, okay, the better performance you get. And with this sad note, I will end up for today. Yeah, thank you.